Today we're going to learn some theorems related to isosceles, equilateral, and right triangles. So it might be good for us to review the definitions of those things. An isosceles triangle, you remember, has at least two congruent sides. An equilateral triangle has three congruent sides. And a right triangle is a triangle that contains a right angle. So if you have not filled out that chart that's the first page of your classwork packet, you need to go ahead and get that done. So let's just hop right in here and start with some terminology. The two angles adjacent to the base of a triangle are the base angles. The angle opposite the base of a triangle is called the vertex angle. So let's look at this. We'll take an isosceles triangle here. We'll say these two sides are the congruent ones. These two here would be the base angles. And this one here those are the base angles. And this is the vertex angle. All right, and so now we have a base angles theorem. It's also called the isosceles triangle theorem. So I may use those terms interchangeably. It's the same theorem, and it says if two sides of a triangle are congruent, so let's mark this, then the angles opposite them are congruent. And as you can see, I had already drawn it that way in my figure next door. But that's all it says. So let's see here. If we got A, B, C, if AB is congruent to AC, then angle B would be congruent to angle C. If two sides of a triangle are congruent, then the angles opposite them are also congruent. And as you might suspect, we have a converse of that that says exactly the converse. If two angles of a triangle are congruent, so in other words, if I have ABC, and if I know that angle B is congruent to angle C, then I know that side AB is congruent to side AC. Converse of the base angles theorem, or converse of the isosceles triangle theorem. Okay, we got another theorem here. Doesn't have a name, so if you were to need to use this in a proof, you would just have to come up with some sort of abbreviation for it. But it says, if a line bisects the vertex angle of an isosceles triangle, I'm going to go ahead and mark this so we know it's isosceles, then the line is also the perpendicular bisector of the base. So let's say I got triangle ABC here, and they're saying we have a line that bisects the vertex angle. Okay, so if that angle is bisected, I know those two are congruent. I already know these two are congruent because I got an isosceles triangle. But what I also know about this line is that it is the perpendicular bisector of the base. So I also know these are right angles, and this is congruent to this. So man, that's a lot of information in that proof. So if, let me write this using symbols, if, and we'll call this line AD since I don't really have a better name for it. If line AD bisects angle BAC, then AD is perpendicular to BC, and BD is congruent to CD, right? It's perpendicular and it's the bisector, which means it divides the base BC into two congruent parts. So there you go. That theorem says a lot. Okay, so now I've got this, and I'm pretty sure I talked about a corollary in a previous lesson, so this is a little bit out of place. A corollary is a theorem that can be proved easily using another theorem. Since a corollary is a theorem, you can use it as a reason in a proof. So our first corollary is, and if you're thinking, well, why is something a corollary as opposed to a theorem? Why is something a postulate as opposed to a theorem? Those are all great questions and something I would encourage you to research. Okay, we got a base angles corollary that says if a triangle is equilateral, so given this triangle is equilateral, then this corollary tells me it's also equiangular. Then we have another corollary that says if a triangle is equiangular, then it is equilateral. So that's the converse to the previous corollary. So this one would say, okay, first I know the angles are congruent, all the angles, and that tells me all the sides are congruent. Okay, then we have the hypotenuse-leg congruence theorem. You will use this a lot, so be sure to remember it. We abbreviate it HL. It's perfectly fine for you to do that in your proof. And it says, if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse and a leg of a second triangle, then the two triangles are congruent. So look at our two triangles here. We got the hypotenuses congruent. We got a leg congruent, and we can see that they're both right angles, so we can use the hypotenuse-leg theorem to say that those two triangles are congruent. So if BC is congruent to EF and AC is congruent to DF, then I know that triangle ABC is congruent to triangle DEF. And let me write a little note here that's really, really important. If you use the HL theorem in a proof, somewhere in your proof, let me see how I'm going to say this. Your proof must contain the statement that the triangles, I'll finish it down here, are right. Very important. If you're going to use the hypotenuse-leg theorem somewhere in the proof, it's got to say triangle ABC and triangle DEF are right triangles. You have to say that. Okay, they got to be right triangles. You got to say that in your proof. The hypotenuse has got to be congruent. One pair of corresponding legs have to be congruent. Okay, so let's do some examples. Maybe not necessarily related to HL, but that'll come in a little bit. So let's see what we got here. We got an isosceles triangle. So now that we know the base angles theorem, we know this angle measure right here is 70 degrees. And let's see. Oh, we got another isosceles triangle over here. So by the base angles theorem, we know that this is also y degrees. And so how are we going to figure out what y is? Oh, I got a linear pair right here, right? So I know the measure of this angle is 110, 70 subtracted from 180. So now what am I going to do? I know that 2y plus 110. I'm looking at this triangle here now. Just looking right at this triangle. And I'm doing the triangle angle sum theorem. It says the sum of the measures of the angles is 180. So 2y plus 110 is 180. So 2y is 70. Therefore, y has to be 35. Okay? Why don't you pause here and try to do these next two problems? Okay, so over here in this problem, I can see that I've got an isosceles triangle, and I'm going to use the base angles theorem to know that these two angles are congruent. So that's why I wrote this equation, that 5x has to be equal to 75. That tells me that x is 15. And then I'm going to use the triangle angle sum theorem that tells me the sum of those angles is 180. 75 and 75 is 150. 3y plus 150 is 180, which leads me to y equals 10. Okay, let's go to this problem down here. I started with the triangle on the right, this one over here. I'll highlight it in red. And what I know is that this is congruent to that. So I know that both of those angles are congruent. They're both 70. So using the triangle angle sum theorem, I get that x is 40. All right, this triangle in the middle now, look at this one. It's equilateral. So the base angle's corollary tells me that it's also equiangular. So I know that all those angles in that middle triangle measure 60 degrees, and I really need that because that's going to help me figure out what this top angle is here in the left triangle. Because if I take all those angles together, the missing one and the 60 degree and the 70 degrees, I know that's a straight angle, so their sum has to be 180. Therefore, 60 and 70 is 130. That means this top angle here has to be 50 degrees. And then once again, I've got an isosceles triangle, and I'm going to use the triangle angle sum theorem to figure out that y has to be 65. If you don't get it, write yourself a note, and we'll talk about it in class. Let's see what we have next. Oh boy, a proof. Okay, let's do it. Statements. Reasons. Trying to prove that triangle RTV, so I got a little overlap going here. RTV is congruent to SVT. All right, and I'm given that RV is congruent to ST, and angle RTV and angle SVT are right angles. That makes me think perhaps I'm going to use the hypotenuse-leg theorem. I don't know. We'll see. That's given. Okay, let me look at these triangles. Well, you know what? It's great because RV and ST are the hypotenuses. So now I'm leaning very strongly towards the hypotenuse-leg theorem because all I need is the leg, right? And oh, look, they both share leg TV. So this one turns out to be pretty easy, but remember what I told you, always has to go in a proof. If I'm going to use the HL theorem, I got to say triangle RTV and triangle SVT are right triangles. How do I know that? Because that's the definition of a right triangle. Definition of right triangle. All right, so now I just need to get that leg, right? Because I've got the right triangle, I've got the hypotenuse. So now I'm going to say that TV, now is it going to be congruent to TV or is it going to be congruent to VT? Look at my order. TV going to be congruent to VT, and that's going to be by the symmetric property. Of congruence. And so finally, after 4 steps, I can say triangle RTV is congruent to triangle SVT by the hypotenuse-leg theorem. I'm just going to put HL, and that's fine with me if you do that too. Okay, look, we're already down here for your practice problems. Let me see how many there are. So those, okay, and then I got a proof, and then I got another proof, and I believe that's it. Okay, my file's acting weird, but yeah, so you got some practice problems. Let's see here. I'm trying to, you know what? I do not want to spoil the fun, so I will put the answers up. How about this? I'll put the answers up for the practice problems and one of the proofs, but I want you to try to do these proofs yourself, and then the second one, we're not going to put the answer up. We'll see how we do in class. So you pause here and work on these practice problems, starting right here with number 4. Here are the solutions for the 3 practice problems. I can see in number 4 that if I say that, if I were doing a proof, of course I would have to say that the 2 triangles are right triangles and that RT is congruent to itself, and then I can see that those 2 triangles are congruent by hypotenuse-leg. In number 5, I got some overlap. I can see I got 2 angles, 2 sets of corresponding angles that are congruent, and so then they both share this side. So I'm going to use the symmetric property to say that that side is congruent to itself, and then by angle, angle, side, those two triangles would be congruent. Okay, number 6, a little bit trickier. I had to use my colored pencils again because you see I got parallel lines here, so I had to use that to help me figure out which angles are congruent. So even though I did that, I've got 2 sets of corresponding angles, but that's not enough. Yes, I do know that does tell me that this angle is congruent to that one, but just like I had in the warm-up the other day, just because I know those 3 sets of corresponding angles are congruent doesn't tell me enough to know that the triangles are congruent. So I do not have enough information there. Okay, and then the proof. So take a minute to look at this. I'm hoping by this time maybe some of you stopped and tried to work this by yourself. So I wrote down the given statements, and then I know that I got to say, I'm thinking again that I'm going to have to use the hypotenuse-leg theorem because I can see that I got right triangles. But remember, I have to state that in my proof that triangle ABC and DBC are right triangles, or I can't use HL. So I put that in my proof there, and then I've got it because I got the hypotenuses. I just got to say that BC is congruent to itself, and finally I can say that triangle ABC is congruent to triangle DBC by the HL theorem. You got one more proof to do. I want everybody to give your best effort to this, and we'll check it at the beginning of next class.